hardware offload API. It's one of the major strengths of DPDK. So it's about RTE flow. I know very well some of the people that worked on it. And the next talk is by Alex from Mellanox and Xing from Alibaba, and they will talk about the scalability of RTE flow in a very huge real-world deployment.
I think it's not, okay, now it's working. So Lingxi and from Alibaba and myself, Alex from Mellanox. Hi guys. Okay, so Lingxi will present a little bit about the Ali Cloud services, just to give you an overview. And what we want to focus is about integration of this activity above RTE flow. There's a lot of work, at least Mellanox is working a lot in the RTE flow area, pushing it forward and doing more and more. We'll present a little bit of performance data that we collected for some of the recent stuff, and try to open some of the topics, concerns, problems that each of us see in this field. Hopefully we'll be able to tackle these in the coming years. So just to recap, last year I gave like this is where we're going to, and we want to do 1 million, 10 million rules and high rate insertion, and there's going to be some issues with how do we cope with all of this. And this talk is actually talking about what we did to try and get this into production, not just during development stages.
Okay, thanks. My name is Li Xin, come from Ali Cloud. This is my first time to English presentation, so I'm not very good at it. So please forgive me for my unskilled. Ali Cloud is a subsidiary from Alibaba Group, which is founded at 2009. So about 10 years, Ali Cloud is focused on cloud computing. And after this year, the Ali Cloud has grown very well over the past years. We have made great progress. We have some very fundamental network service, like, for example, the VPC, SLB, CEN, and SAG. We provide a lot of network features to our customers to make them use our cloud in a more easy way. With this opportunity, I wanted to say thanks to the DPDK community, because the DPDK technology is widely used in Ali Cloud network platform and our customers' application. So I think I should say some thanks to the community. As the business grows up, the very high network performance is necessary. For example, our VPC gateway and NFV gateway will takes huge traffic, up to about hundreds of mini per packet per second. So the high network performance is very necessary. And another story is that another scenario is that the video industry is booming in China today. So there are a lot of startups focused on online education, short video maybe, and live broadcast. All of this industry require very high network performance. And another scenario is from our Alibaba Group inner customer for our e-commerce. Each November 11, we just call it a single day. It's similar like the Black Friday in Western world. It's a shopping festival. It's a shopping festival. In in the Double 11, we call it Double 11 or single day, there will be hundreds of million people will join this shopping festival. They will make several billions orders within 24 hours. So this will be a big challenge for our trading system, including some database or some messaging middleware. What's more, all of this trading system is built on our cloud platform. So the ultimate network experience is very necessary for us. Before we start the integration work with RTFlow, let me just introduce some basic concept for the VPC network. As the figure has shown, the first thing when the packet is input into the VPC network, the first thing is to do the parser. We can get some basic information like untupper, like some user-defined metadata from the packet head. Use this necessary information, we can build a unique key for every packet. And then use this key, we can do some flow lookup. If the flow lookup hit, we can get some more expanded information, which will indicate how to do the packet action, which includes some counter, meter, or some kind of tunnel operation. Then we can just send this packet out, use the chosen report. The VPC provide a fundamental network service which can provide each customer a single isolated network. So as we know, there is always a trade-off between the network functionality and the performance. We use our current software system, we can get a better rich feature, better poor performance. Use current, just use hardware SRV, we can get a very high performance, but we can get a very rich feature. But these things had been changed because more and more smart device or some programmable ASIC or some new kinds of performance need can support network acceleration. So the hardware acceleration plus SRV may be a good solution for our scenario. But there still have a lot of challenges to integrate this work. For example, how to satisfy the large-scale flow entries, how to ensure the flow timely insertion, and how to aging hardware flow, how to implement hardware state machine, and how to be comfortable with this different kind of hardware. We do have some cooperation with our vendor and supplier to enlarge the flow entries. We need at least 4 million flow entries in our system because our current software system has already touched this level. So we also do some workaround for this for some hardware can't provide this flow entry. For example, we implement a mechanism which we call flow rebalance. We can monitor all of the flow entries and just offload this flow has big bandwidth to save the flow entries if the hardware cannot support enough flow entries as we need. And the flow aging and insert rate is also a very important indicator because this will impact the indicator that we can the new connection, if the flow insertion rate is too low, we can't establish our new connection at the same in time. So we need at least 200K flow insertion rate. This is our current software baseline. So we may need more large. As we know, the hardware can do something simple but very quickly. The software can do something complex but more frequent. So we just make the software to manage all of the complex states. All of the TCP with special flags will be sent to the software to process. And when the state changes, the software will notify the hardware. The design principle is mostly like this. We will send the flow to the hardware as late as possible and delete the flow from the hardware as soon as possible. Then we can make the software to manage all of the complex state and make the hardware more simple. There are a lot of vendor and hardware can support acceleration today, but they have different vendor API and a different feature list. So we use abstract layer to shield this different. We call it Xflow. So use this Xflow, we can also do some quick response for the online system issue. We can do some bug fix very quickly and work around before the community. And the Xflow also call the community RT flow interface.
So part of the layer that Lixi was referring to abstract into different hardware layers, not everything is available in RTE flow today. And in order to allow this integration, we created a private layer which helps bridge this gap. The plan is to take all these features and slowly push them upstream into the general RT flow and DPDK community where needed. Part of it is the way our NIC is designed with steering, where we have separate RX and TX domains. And their virtual switch is looking at this as a switch. So if they want to go from vPort to wire or wire to vPort, that's simple. It's an RX only or TX only rule. But if it's a vPort to vPort rule that they want to offload, so we have to insert the rule twice and hide this from the application. That was part of the solution we agreed on. An additional solution was an additional feature that we had to add is rule aging. How do we track activity or inactivity of specific flows? How do we monitor this in large scale? Because RT flow is very defined for single flows. So rule or RT flow aging or rule aging is something that we're working on to push upstream now as well. And the last part was a flush of full, what Lishi was referring to is batch delete. If you have a VM and it has 10,000 rules, you want them to, when this VM is migrated, you want all these 10,000 rules to disappear immediately. You don't want to for loop on 10,000 rules and find them. So some way to map some metadata to all the relevant flows and then get rid of them at once. So these are the main things we added in this layer, and the idea is to push them upstream now that we have a stable solution. Another major part was how do we reach very high rate insertion? So most of you, when you think of DPDK, you take VFIO and take the device, the whole PCI device, into user space, and there's one process managing this. Mellanox devices work differently. We have what we call a bifurcated driver. So the PF or VF always has a kernel driver instance. There's always a netdev interface associated with this. So we always have the kernel driver exposing this, and through what's called in the Linux subsystem, the RDMA subsystem, we have an RDMA device which exposed to user space, and then our PMD uses the RDMA core library to access the device. So the legacy steering solution we had was application goes to RTE, flow goes to our PMD, which calculates what needs to be done, sends the system call to the kernel driver through the IB layer, through the RDMA layer, goes to the firmware which manages the steering, and then sets the steering in the chip's memory domain. So there's steering logic in the firmware which manages the hardware. And what we did here, we actually exposed islands of this steering logic to user space. So there's some things that the firmware still manages in order to isolate this process so it won't ruin and won't hurt anything. And once this is exposed, we have now similar logic in user space, which can write directly to the hardware memory and manage rules on the relevant domains, match criterias, actions, and whatever is needed. Some of the resources which are still low rate accessing, like accessing a vport is not something that you do often, or configuring an NCAP header. There's probably much less NCAP headers than specific rules. So these still go through the legacy path, but a lot of the logic is directly managed from user space now. So this allowed us to bypass a lot of the overhead we had in the legacy driver, and now we can reach very, very high steering rates. Some of the drawbacks of this is that we increased the memory footprint here in the user space process. This is one big process. So a lot of the steering, and if you're talking about 2 million, 4 million rules, that's a huge amount of memory. But it allowed us to adapt our steering design to fully utilize what RT flow exposes. RT flow exposes groups, which allows you to actually build a multi-table hierarchy of steering. RT flow doesn't limit a group size, so our new steering design allows to dynamically resize the steering depending on the amount of rules that are added. We can design different kind of hierarchies. So, for instance, deleting a VM, if we have a dedicated table for a VM, just deleting the pointer based on the VNI into that next table, with one rule, we disconnected the entire VM steering domain. And then we can slowly clear that. Okay.
Okay. After the integration work, we have got some very exciting data. Firstly, we do some comparison between the hardware acceleration and the software forwarding. As the figure shows, all of the important data indicator, we have got a significant improvement. We can get a 37 million packet per second use this hardware acceleration, and the TCP latency we can get a latency as low as 7 microsecond. This is a one-way socket perf ping-pong testing, and the hardware bandwidth is also have a significant improvement. Then we have to also do some comparison between the virtual machine and the physical host. I think our customer will be very interested about this comparison, because there is always a thing that the cloud network performance is more weakly than the on-premise native server. So after that, things have been changed today. After using this SRV and hardware acceleration, the virtual machine network performance is very closely to the physical host. we can get the same performance. Yes.
This is a little bit more benchmarks on the low-level drivers that we have on the PMD. This benchmark shows the scalability with multiple cores. In this use case, we took a very simple 5-tuple rule, no tunneling, and a very simple action, so the steering insertion can really be efficient. Most vSwitches, including the Alibaba solution, is single-threaded, but if we scale to multiple cores with the insertion rate, we can, you see that this can scale pretty linear, and we can reach more than 1 million updates per second. That's updating, insert, or remove of rules in the hardware itself. And then for a more generic cloud solution where we have overlay, for instance, VXLAN network. So there are 2 examples, one for the transmit rule from a SRV to the wire, or wire in the receive from the wire to the VF. So these have both more complex rules. Some of these can reach up to 12-tuple members that break up to multiple insertions in the hardware. They have much more complicated actions. You want to count, we want to do some routing on the way, so we want to modify the headers, change inner packet MAC addresses, IP headers, want to do the NCAP if it's on the transmit, or DCAP on the receive. We might want to mark this if this is going to the software for the first packet. So we have to mark the packet. So these are much more complicated rules and actions, and this comes to show the scalability. So definitely the results go down, but they're still pretty high, even when we have 2 million rules, and some of these drops are due to the resizing of the table. We start with small tables, and when we see that this kind of tuple is increased, we start to increase depending on where the entropy of the rule is. If the IP changes, if the inner IP or outer IP changes, so different parts of the flow tables have to increase, and we don't want to spend too much memory. We want to be efficient in memory. So there's gentle dynamics, when to increase the tables, when to keep them small. Okay, so some of the things looking at the future. So obviously, Keith was talking about counters, and we had a couple of sessions, RT flow as well. It's something we're looking at. What sort of debuggability, and if we have 4 million rules, it starts to get complicated. And if we allow more complicated actions, and OVS DPDK, for instance, has the method of connection tracking, which uses some recycling, which means you actually go back to a previous table, which could cause a loop. And if we want to be able to debug all sorts of scenarios, so we have to think wisely on how do we expose debuggability capabilities to RT flow. Obviously, going to production, a vendor needs some sort of visibility into what's happening.
Some requirement for the flexibility of the network queue and network interface, because there are so many kinds of instance type in our online system. So we want to have more flexibility for the network queue and the network interface for flexible allocation. Then the different instance type, we may have different interface queue numbers. The second requirement is that helping mode for the NFV. In the NFV scenario, the packet was input into the VM, and the VM will do some packet change and then turn back this packet to the network. If the helping mode can support in the NIC or the hardware, all of the traffic will be turned back, won't be sent to the VM. So this will be this can be reduce a lot of CPU VM CPU cost and will make the latency and throughput data will be more better. And the third is the firmware hot upgrade. This story is that we always need to upgrade our application, and this will make cause we should do DPDK version upgrade at the same time. For example, today we use the DPDK version 17.11. Maybe tomorrow we want to upgrade it to 18.11. This will make cause some NIC firmware can be compatible problem, because maybe the 8.11 DPDK version need a new firmware, NIC firmware, but this will be a big trouble for us because our online system can't do the firmware hot upgrade. That means we need to shut down our current running virtual machine to do the upgrade. This will be a big trouble. So we just propose the firmware hot upgrade function for the cloud environment.
So actually, these are not necessarily related to RT flow, but they're more related to going to production with DPDK. We talked about ABI compatibility moving forward, and it's not just the ABI for the application. They have this shim layer to take different kind of DPDKs maybe easily, but if our PMD requires a firmware upgrade, then it means their service is going to be killed on that machine, which is something that we have to figure out. And then, I mean, we have a very strong NIC, but even that is not strong enough. We do have enough counters to count each of the 4 million rules we're entering, so we have different counters. Just reading all these counters to Userspace in order to do aging is a feature by itself, but we don't have enough flow meters. We have very limited amount, and we have to see how to move with that forward. So we're adding new hardware and resources to enhance even more the flow steering capabilities with more hardware resource. One of the major, by moving all the management of this flow steering insertion update into Userspace, as I mentioned, memory footprint of the Userspace process really increased. It means that they can sell less memory to the VMs. It's a problem. So we have to figure out how to reduce. Currently, it's somewhere around 4K bytes per rule. So that's multiple gigabytes for the system. We're looking at different layers, obviously, also our code to improve data structures and reduce them, and reference and locks and whatever needs to be done, but also some of the work we're looking at is reducing caching. Today, each layer of the application, RTE flow, PMD, driver, everybody holds a cache of this is what the rule is, and this is the metadata or the match criteria. We're going to suggest some solutions which will reduce in every layer that we can the memory footprint in order to scale really well. So that's one of the major topics we're looking at. Questions? Yes, microphone? Allow me. I don't know if it's working or not. Check.
Yep, this was good.
Okay.
Yeah, hey, great job, guys. Really, always good to hear from customers, right? And fantastic job presenting not in your native tongue. So thank you so much. Couple of questions. So the appliances, right, that you put up at the start, I'm assuming that those are sort of your internal infrastructure, right? So this is what you use to steer and inspect and mirror traffic into your infrastructure within Ali Cloud, right? Am I assuming that is that correct?
Yes, this has been great scale, and will in our plan will go to our production environment. Yes.
Fantastic. And then I have a question on the your RTE vSwitch proposal.
Okay.
So you have so right now, how do you handle multiple requests to the device? So in other words, you're going to have multitude of virtual machines, and you're running multitude of DPDK instances. I'm imagining, and then you're going to add you know, you're going to make a multitude of requests into the IO device.
So there are two answers. First of all, the vSwitch layer is just to translate features that they want to see all vendors aligned. So some vendors didn't give a DPDK RT flow directly, they gave some other solutions. So it was more of alignment to make sure each vendor sees the RT flow in a similar way. Today, the application is a single-threaded. From control aspect, it's a single-threaded. So actually, each rule is entered once. The way we implement it, it's just very high rate. It reaches like around 350,000 updates per second, give or take, depending on the type of rule. So it's a single-threaded insertion. It's actually asynchronous. We do all the calculations we need until we know the rule can succeed and is valid and can succeed, and we queue it. And it takes, depending on so it can take a couple of microseconds maybe to update. Some of this is done in batches, and there's some caching that our device has to refresh once in a while. So another packet might come by before the actual rule is there or removed.
Got it. Okay. Okay, I have a lot of follow-up questions, but I'll leave it. We can do that offline.
Okay.
So one more. So you had one specific component that's gonna carry out the configuration request, right? So now imagine you're gonna get a multitude of requests. How are you going to arbitrate between who has certain priorities, certain policy, who is allowed to do what? How are you going to set it?
You're referring to the bifurcated solution?
Exactly.
Okay, so basically it's up to the application vendor. By default, the rules are not, or the application, for DPDK we implemented promiscuous mode because that's how DPDK works, but we have this steering technology before entering the DPDK world. Basically, the steering technology always says, put your tuple in the right priority, and our driver defines some levels that you can define, that you can use. But if you would take two different applications, two different DPDK applications, and they're not aligned in how they manage the priorities, you'll probably get a mess, or one of them will win and the other one will lose. So if anybody catches the uplink in promiscuous at high priority, he's going to win. The other one will not see any packets. But in most cases, it's not just random applications going on the machine. There's a manager, the hypervisor, or virtual switch that manages this. Other solutions might be multiple instances of DPDK, but it's usually the same business logic that's running. So each one would take a different IP address, so it's not promiscuous, it's just match on source IP, dest IP, or whatever. You can look at it as similar as doing RSS, and you have multiple cores, so they defined how to separate the traffic into multiple queues.
Got it, thank you.
Okay. Thanks.